So, really hopeful that more people were sticking around, but oh well, let's go and see who filters in afterwards. So, as the title may be a little bit vague to most of you, it may mean a lot to some people in specific areas of software development, but anyway, I'll touch on basically everything necessary to fill you in on what this is, and also basically, as this is a talk about the software architecture of one of our products, we do hope is you kind of show some interest and you decide to take a look at what we've been offering. Okay, so just for an introduction, so BIM and Scan Limited is an Irish company that conducts a lot of R&D in the areas of scanning and building information modelling. I myself have been there 3 years and I've been shepherding a lot of the software development that's been occurring in our company through its phase from initial experimentation all the way through getting a fully fledged product out there in the wild. And that product, in the second point, is what we call BIM and Scan AutoCore, which is a cloud-based software tool that allows users, after they've signed in, to basically upload their BIM models and laser scan point clouds and perform analyses on them to show what appears to be corresponding between the real world and the virtual. So, like I said, it's a cloud service, and it's available to anyone who's interested to take a look at. You just go and show your interest in signing up for some kind of trial, and your way you go. So the topic of this paper is about our software, but more importantly, the adaptations we made to it as it evolved. Specifically, the external memory solution, which I'll touch on now in a sec, and the testing we did to show what was our need for it, and how did we evaluate if it was a worthwhile thing to do, and our results and conclusion. So, firstly, the problem domain our tool addresses is in AEC Industries. How do we assure that what was built on site is what was designed, which has been a problem ever since you've started putting marks on paper. So a lot of people want solutions to this, and a lot of people go about offering prospective solutions to this, and we think ours is a very good candidate for being one of the top ones, because basically we're in the business of trying to assure stakeholders that what was built is an objective fact, that it lines up with exactly what they wanted and what they had in mind. And the way to do this is through open standards and some algorithms we've developed that help analyze the data stored in these open standards. So BIM and Scan AutoCore, like I said, is a cloud-based software service, performs analyses between models, IFC, building information models. So basically any file, any model that has been exported out to an IFC formatted step file, and point clouds in E57 format, which is another open standard that is widely used and supported by BIM authoring tools and viewers. And what it does is it reports correspondence between the real world built environment and its virtual model counterpart. It's available from our website, bimandscan.com, for users to try. We've been in the process recently of revamping our website, and we're continually improving it, so we're hoping it looks a lot snazzier and you get more interested in what's being offered. There is just a screenshot of an example user specifying a job to run by providing his inputs and getting ready to load it. So some example results. So we provide 3 kinds of results. We provide a BCF report, which is a common open standard for interacting with issues and tracking them, which is used in a lot of tools nowadays, automatically generated. And we provide a color-coded E57 point cloud, some examples of which in a previous slide. And here you see where the red is highlighting areas that are non-corresponding outside of a given tolerance. So once you've aligned your model and point cloud together and run them through our tool, what you should see is the key areas pointed to you visually and through the topics created in the BCF file that you can jump to camera viewpoints at for where things might need to be adjusted or might need to be revisited. So the history of our software, the first version, which sprang out of the R&D we were doing in 2017 and earlier, was a command line executable. So basically it ran on desktop for one user. It was basically used by myself and those I trained in our company to use it, which made it was hard to install and deploy elsewhere. There was some dependencies to get through, and you needed to basically walk someone through how it was used. Second version, which is the first one, which is on the cloud, was made available to everyone, and it's more user-friendly than our previous one, which was typing in commands into a terminal and hoping for the best. But the third version is basically a better backend for our cloud service, which is the external memory system, which I'll address now in a sec. So the challenges we faced moving our software into the cloud, because it was originally a single user command line prompt, We deployed on Microsoft Azure using two technologies, Docker and Kubernetes, as a system for orchestrating the executions. So basically every time you queue an execution to run, it's those tools that would manage it. So in the cloud, if you use the cloud infrastructure on any services like Microsoft or for Amazon, your available performance, so your RAM, your CPU size, hard disk capacity, that all comes at a premium, and it can be quite high, especially for RAM and CPU usage. So an external memory integrated into software was our goal to help alleviate costs, and we want to know, did our improvements achieve what we wanted to achieve? So what is external memory? So when you use a computer, you have your main memory, which is the RAM, which is typically what is somewhere in the range between 8 to 16 gigabytes, much higher on workstations or machines that you put more money into. But that's the working set of memory. So basically any software that's running now is operating on the RAM, it's storing its data in the RAM, it's accumulating temporary values from what it's calculating at that current point in time in that area. So the external memory is a concept that basically extends the memory space into the hard disk. So instead of just using the fast RAM, it pushes data onto a file, a special cache file on the hard disk. Now, operating systems like Windows or Linux provide a functionality to do this. They will do this automatically if they see that you're using too much memory, and will try and push things off into a paging file or a swap file, as it's swap partition as it's in Linux. But basically this is used to handle data sets larger than what can fit in RAM. So what we used this idea for was, instead of just letting the operating system try and struggle and work out what's going on, we integrate it directly into our software. So this kind of integration is applied currently to high performance computing, anything dealing with a lot of big data, and distributed computing, which rely on large data sets and processing them greater than any one computer could contain. So we saw it could lower our memory footprint and therefore cost, so we jumped on it and decided to start experimenting with it. So what we did was, our software is written in a programming language called C++, which is a fairly standard one for systems programming, but we found there's a library available, the standard template library for extra large data sets, which basically provides this functionality that we could try and integrate. So basically, our data structures are being built on top of this technology. That means that intelligently it tries to cache data that it doesn't think is being used right now onto the disk, keeping only the important data it's working on at the moment in memory. So the goal of that library was to try and maintain performance either similar or as good as possible compared to using a program that ran directly in RAM. And where we were particularly interested is sequential streaming of data. So basically running through an entire data set from the first element to the last, just streaming the data from the disk into memory, processing it, storing the results out. That's the fastest possible way it could work like this. So we decided to try and adapt our algorithms to this. So our algorithm samples the pointlets, basically reduces the input data set for size considerations, but maintains the same physical structure. And it performs ray casting, so basically projecting lines and rays in 3D space, and on the intersections handles those, interprets them and processes them into a new data set, which does incur a lot of memory usage, especially if the input data set's very big, because you're effectively casting one ray in 3D space along a direction for every single point in that data set. All right, so if you've got millions of data sets, you've got millions of rays, and you need to handle that. So ray casting was an obvious thing to try and do this adaptation to. And the diagram here is just a very simple, assuming a buffer size of 4, which is minuscule in real life, but it's showing the flow, which is basically you iterate from A to B in your positions, and you pull that data into a temporary buffer, you raycast that information, the results you're accumulating, you push into a similar data set. The yellow data sets here are color-coded, they're the ones we could adapt to use external memory. The blue has to stay in main memory, because that's what the raycasting system uses. But when it came to, comparing this with our hardware, on the cloud, we basically had to allocate 8 gigabytes per execution of memory based on common use cases we found with the input data sets we were receiving. The cloud virtual machine, so basically the computer that was actually running it on the cloud, had 32 gigabytes. So assuming you could subtract some from the operating system and the management software, you could roughly run 3 executions at a time on the one machine. Now, our software is designed to scale outwards, so every time it overflows, it allocates new machines automatically, or new space automatically to perform this computation, and then when it's done, it cleans it up, and then we're not paying for it anymore. All right, but the external memory, after our initial investigation, showed that we could drop our execution down to only 2 gigabytes overhead, keep the 32 gigabytes RAM on the VM, and get 15 possible as the theoretical upper bound for executions shoved into the one machine. All right. So that looked very promising. So what we did was we adapted our software and we started running tests on how this would work. So we deployed it 2 times. We did it locally on a desktop. So basically using the command line like before and giving it unlimited RAM to see how much it actually ended up using. And in the cloud, which was the standard method for user submitted executions, which was a fixed amount of memory, which was the 2 gigabytes as mentioned, or 8 gigabytes for the old version, 2 gigabytes for the new version. And then when we measured what was happening, we did this by taking per second snapshots of the performance characteristics of the execution, i.e. the container that is holding that execution. And for the cloud, we used timestamps from the start and the finish end time of the job, and we just computed how long did it take. So basically, we wanted to see, could this work reasonably within the timeframes we think it would gel with our existing software. So if our existing software took 5 minutes to run, could we get it to run not more than 10, or not more than 30? Or, what's the worst case or best case scenario out of that? So we tested some large data sets we had used before, and I'll show you some graphs now that show there's a variance between the type of data set being used, the structure of the data, and how it actually behaved in both versions. So the first one, and if you see my very clever attempt to stick the graph in the whole slide, is what we call the plant room data set, and it was 4.5 gigabytes in size as a file. The orange is the old version, which is the version that everything's done in memory, and in the blue one, that is pushing data onto the hard disk until it needs it. All right, so you can see it's basically double, and there's a huge spike up to about 3 gigs or higher on the old version, but the new version sticks within 1.5 gigabytes of usage, and this is without trying to cap it. This is just naturally it was able to keep it that low, just on its by default behavior. You can see that it basically spikes up, and then in the original version it's finished, and in the new version the same computation occurring in that spike is basically plateauing for a while, and then it finishes. But within about the same, or within 50% of the time, or 150% of the time, it was working that way. The next data set says something similar. It's a hotel data set, 7.6 gigabytes in size, and what happened in this case was didn't use a lot. Even though it was a larger data set, the structure of the data meant that its analysis didn't kick too much into main memory. So you can see here that the 2 gigabytes is the largest unit on the y-axis, and you can see they're quite close together. The external memory still took half as long, but kept itself below 2 gigs. In our old system, if we'd capped everything at 2 gigabytes, that spike would have just caused a memory allocation error. The program would have just crashed because it had nothing to save its data to. And the last one here, which is the most interesting, is an office floor, which was 6.1 gigabytes. But you see here the variance we got in testing. Here in the original version, we hit up to 7 gigabytes of memory in use, but it finished far, far faster than the new version, the external memory version, which was stuck at a 1 gigabyte with a slight trough at the bottom at the end there. And this is very interesting because that looked like to be our worst case scenario, but even still, we were able to keep it within 2 gigabytes as our overhead for the new version. So our observations were approximately double time taken on average, but sometimes 75% in worst case. But it did give us a huge reduction in the amount of memory being used by the process, which meant that we could try and jam more into the one area, one machine. That table there is basically how much faster the in-memory version was compared to the old one, the external memory version. So basically the office floor is the worst case. But funnily enough, in the cloud, for some reason, because of the allocation, the pre-allocation to set up and run the job, and then the cleanup of the job afterwards, it actually evened out. So it looked like it was similarly a 50% spread, which from a user perspective would actually not look very different. We just said it'll take a little bit longer, but it'll still run, and you'll be able to pack more in. Then it looked perfectly fine and consistent. So what we did was we took this information and we started working on it. For example, we took the plant room and we did some throughput estimation. So that's just capacity divided by duration. So we've two sets here. So we've got the old version, the new version. We could fit 3 in the old version per VM. We could fit 15 in the new version per VM. And we divided that by the time it took to do the whole job. So we got an execution per second throughput, and then we have makes more sense to turn it into minutes, so we have that. But what you can see here is that even though it's double the time taken, it's double the throughput, because of the increased parallel jobs running at one time. So if you took 50, 100, 200 jobs and you submitted them to both systems, and we controlled what was being allocated, so for example, just 3 for the old system and just 15 for the new system, you'd see that twice as many jobs would complete in the new system overall compared to the original, which is a great improvement for us, because that type of scaling costs us money to do, and we need to make sure that what we charge users can actually cover the costs of what they're incurring when they run their analyses. And this is a great improvement to that. So what we concluded during this was, despite the longer execution times, we got more performance out of the cloud system because our throughput was massively increased. And it also made the most of what we had already put on the cloud without needing to scale out to any larger sizes or new VMs. More executions in a single VM meant lower cost per execution, which meant it was also more viable for us to expand the amount of users we're trying to pull in, because they won't kick us into hitting too much expenses until a certain point, and that's been pushed way down the road. Scaling cost is effectively controlled. So I know that talk is quite technical and a lot more related to the development and architecture of a particular software solution, but we do believe for anyone who is interested or is indeed a software vendor themselves or works for one, that they can basically apply the same strategies when working on cloud infrastructure to try and bring down what they're spending. And for those of you who are just interested in the side of the software, the client and what it does, if you're a client or if you're a contractor and you want to introduce this into your workflow, our website is bimandscan.com. Like I said, we've been busy revamping it, and we've been expanding our reach. So basically we're trying to reach more people, get them on board, see how they like it, see what testimonials we can get out of them, because we have some existing customers that are already happy with what they've got, and we just want to keep improving what we're doing, because we see that this is a very valuable tool for everyone. Thank you. So, questions?